Hi everyone, let us discuss an interesting topic in 9th class physics, which is called rotatory motion. So, before going to learn about this rotatory motion, let us have a discussion regarding motion, so which is called introduction to this lesson. So, introduction to rotatory motion. So, what is motion actually? If an object, for example, let us take this duster. Now it is in the state of rest. After 1 second, 2 seconds, 3 seconds or 4 seconds, this will be in the state of rest only. Means it is not changing its state with respect to time in this reference frame. Let us consider this room as a reference frame. This object called duster, it is not changing its state with respect to time in this reference frame. Then this body is said to be, duster is said to be at rest. For example, the same duster is moving with respect to time, means it is changing its position. Initially it is here, and after 1 second it is here, and second here, third second over here. If it is changing its position with respect to time in a reference frame, then this body is said to be in motion. How many types of motion are there in our nature? So, this motion is classified into 3 major types. The first one is translatory. So, already we have discussed about this translatory motion in earlier classes. Let us have the definition of this translatory motion. If an object is moving as a whole, if the object is said to be moving as a whole, then the body is said to be in a translatory motion. Best example, this one only. If this rigid body, if I apply force along the length of this duster, this rigid body will be moving along a straight line. Means all the particles of this duster is said to be having the same type of motion, same linear velocity. So, this type of motion is said to be translatory motion. Next, the second type of motion is rotatory motion. Rotatory. For example, the same duster will take, and let us fix this duster at 2 points. Next, try to apply the force perpendicular to the length of this duster. So, I am applying the force in this direction. Let us discuss the motion of the object in this case. This is the fixed position, and then I am applying the force over here. Then observe the motion of the body again. So, here all the particles of this duster is said to be moving in the circular path. If I can continue like this, all the particles will be said to be moving in circular motion. All the particles will move in the circular path, except the particles which are in between my 2 fingers. I held these 2 fingers here now. So, these particles will not have any rotation. Best example, the fan. When we switch on the fan, what happens? The fan blades will be rotating except the center of mass of the blade. So, in this type of motion, few particles will be at rest and the remaining particles will be moving in the circular path of different radii. If we take a particle over here, this will be having one kind of radii. If I take a particle over here, this will have greater radii than this. If I take the least foremost point of this duster, it will be having the maximum radius. This, and then this fixed point is said to be the axis. The line joining all these fixed points is said to be axis. So, in this rotatory motion, 2 points are very important. The axis about which the object is rotating, and the particles. The motion of all these particles in circular path, and the particles which are lying on the axis will be having the stationary state, right. This is rotatory motion. And the last one is oscillatory. This we are going to learn in future classes of this class, but let us give an introduction to this. The same duster I am taking, I am holding this duster like this, like in the second case only, but if I apply force, or just if I draw this duster to left and right like this, so this duster will be making in motion like this. So, if performance of this kind of motion is oscillator motion. Best example, simple pendulum or the pendulum in the clock. In the pendulum clock, the pendulum will be having the oscillatory motion. So, let us have the introduction once again. If I apply the force along the length of this duster, we observe translatory motion. When I held this duster like this and apply force perpendicular to its length, I observe rotatory motion. And when this duster is held like this freely, and then if I apply force like this kind of motion is said to be the to and fro motion of the body is said to be translatory motion. And our interest is rotatory motion in this class. So let us discuss what are the different things in the rotatory motion. I think we have already learned circular motion in some earlier classes. So the same topics will be repeated over here. So let us have the introduction regarding the circular motion once again. And before going to learn this rotatory motion, why should we learn this rotatory motion? Let us have that. Okay. For example, if you want to open the door or close the door, everybody will go and apply the force at the edge of the door only, because of doorknob will be present at that point. But the actual reason of that is, when you apply the force at the doorknob, it is very easy to close the door or open the door. But once you move away from the doorknob to the hinges, we can close the door, but with a great effort, means we have to apply more force. But when we apply the force exactly on the hinges, we cannot close the door. Why? The reason will be explained in this lesson. Once again, for example, if a swimming pool diver is jumping from the jumping pad, when he jumps and when he is flying in the air, initially he stretches his body, and once he is in the air, he squeezes his body so that he will be having more rotation, angular velocity, and then while he is jumping into the water, again he stretches his body. Is there any reason for that? Yes, there is reason that we are going to learn in this lesson. Once again, for example, if the total ice present at the polar regions is melt and the total water is coming into the equatorial region, will there be any change in the rotation of the earth, in the time period of the earth? That kind of new interesting things we are going to learn in rotatory motion. That is our interest. So before going to learn about rotatory motion, let us have a study about the circular motion. So let us consider a body of mass m is performing a circular motion. Initially the body is over here at a point P naught, and after some time t, the particle is observed over here as it is having anti-clockwise circular motion. And then if you join these two lines, initial lines, this is the position vector of the body, and here one more one, and let us consider the center as O, then it will describe some angle at the center. So let us discuss what is P naught, what is O. O is called the origin, our reference point. Next, P naught is the initial position of the body. Next, P is the final position of the body. These are the positions of the bodies, linear positions. And what is this theta? So this theta is described by this vector, the radius vector, which is joining the center and the initial position, the center and the final position of the bodies. So this theta is said to be the angular position of the object, angular positions of the body. Okay. So let us consider S distance is described on the circular path. If the radius of the circle is r, then the relation among S and theta and r can be written as S is equal to r theta, then theta can be written as S by r. So this position or this angle is called as angular position, or this is also described as angular displacement in the rotatory motion. So as we have observed here, the S is measured in meters and R is also measured in meters, and this is dimensionless quantity, means it will be having the units but not dimensions. Its practical units are degrees and revolutions, and its SI unit is radians. So let us discuss the same concept in the rotatory motion. For example, let us consider a rigid plate like this. So I am going to rotate this rigid body with the help of this fixed point, means this is my axis of rotation. I am going to rotate this object about this axis. So as we have discussed about this rotatory motion already, this topic comes under rotation of a rigid body. So, I have taken a rigid body and then I have fixed one axis over here. I have taken this axis and I am going to rotate this in an anti-clockwise direction. So, my interest over here is, so I have to observe a point called like this, a point is here. I want to observe this point. So, as I told you earlier, if it is the axis and if I apply a force like this, all the particles on the duster except the points lying on the axis rotate in the circular path. In the same manner, even this point will be rotating in a circular path. Let us have the three-dimensional view. So, this is the dotted line. These dotted lines will show you the motion of this particle. And then, if I join this line, this is the position vector of that one, radius vector, and initial position of this one is P naught. And let us consider after some time over here, the particle is reaching a point called P. If I join these two, it will be describing some angle over here. That angle is called theta. As I told you in circular motion, that is called as angular position. Here we call it as angular displacement. Angular displacement. And it is denoted by a letter called theta. So, again in the same manner, let us take this as S and this is R, and the relation among this one is S is equal to R theta. In the same manner, theta is equal to S by R. So, it is dimensionless and its units are SI unit, radians, and practical units are revolutions or degrees. And this physical quantity is called angular displacement. Is there any reason calling as angular displacement? So, whatever the thing, whatever the distance described over here, it is the distance denoted by S, and we are denoting the same displacement or the distance with respect to this angle, in terms of this angle. That is why we call this as angular displacement. And this is one way of telling the position of the particles which are performing rotatory or circular motion, because circular motion is a special case of rotatory motion. That is why we call it as circular motion is a special case of rotatory motion, as all the particles except the particles lying on the axis perform circular motion. Next, so let us discuss about this one. So, if I take another particle, some other particle over here on the same line for the same time, it will be rotating about like this. Means clearly this figure will show you that the whatever the particle I have taken, first particle is this, and the second particle, if I take another particle, third particle, for the same time the rotation of the body will be like this, and clearly it will show you that the angular displacement of all the particles of a rigid body which are away from the axis of rotation are same. Means angular displacement of the body will be, of all the particles of a rigid body will be same, but especially for rigid body only. If it is not a rigid body, if it is non-rigid body, what will happen? So, if it is non-rigid body, the angular displacement of the body which is away from the particles which are away from the axis will have more angular displacement than the particles which are close to the axis of rotation. Means this more is the distance, more is the angular displacement of the bodies. So, here it is clear that here it is measured in meters and R is also measured in meters, that is why it is dimensionless. So, angular displacement is a dimensionless physical quantity. Clear? And this is the thing. For example, if this angular displacement is very clear that I have taken some part of this motion of the body, rotation of the body, with respect to time, I think this theta will be changing, right? After some time t, this is observation. After some time t1 or t2 like that, the theta will be increasing. theta will be changing. So as this theta is changing with the time, we can introduce one more physical quantity called angular displacement, angular velocity, and which is denoted by a letter called omega. All these things which we have studied already earlier. So displacement, you know the term, and velocity also you know the term, and this topic already we have studied in the linear kinematics. But only thing is, this is the rotational kinematics. As we are discussing about displacement, velocity, and then we discuss about acceleration, and this topic is also comes under rotational kinematics. Rotational kinematics. So whatever the things you have learned in the linear kinematics will be repeated in the form of analogous quantities here. So earlier we have discussed about velocity. The rate of change of displacement is called velocity. In the same manner, the rate of change of angular displacement is called angular velocity, because this theta will be changing. This theta, angular displacement, will be changing with respect to time. If time is less, theta will be less. If time is more, theta will be more. It will be changing. If it is changing, then we can introduce one more physical quantity called angular velocity. So simply we can discuss about that angular velocity. Omega average means average angular velocity can be written as, for example, if I take some other situation called theta 2 or T2, then this angle would be called as some theta 2. Then omega average is equal to theta 2 minus T1 by T2 minus T1, or we can write simply the time period T, if it is called as T1 and if this time period is T2. So simply the average velocity of a rotating body or particles in the rotating body, rigid body, is nothing but the change in displacement, angular displacement by delta theta by delta t, simply. And in kinematics, while we are learning about velocity, we discussed about types of velocity also. One is average velocity, and then we discussed about instantaneous velocity also. So what is that instantaneous angular velocity? The velocity, angular velocity of a rigid body or the particle in the rigid body with respect to or within that particular instant of time, at that particular instant. Means what's the meaning of that? This time period should not be bigger. The time period should be a very small one. At that particular instant means at that particular second or the particular time, point of time. So we have to limit this delta t. Means we have to limit the delta t to very small value, but not be 0. So that's why we use limits. Limit delta t tends to 0, then delta theta by delta d. This is also called as, all represented by d theta by dt. So these are the different types of velocities, angular velocities in the rotational kinematics. So rotational kinematics, first we discussed about angular displacement. As this angular displacement changes with the time, we introduced one more physical quantity called angular velocity, which is denoted by omega. Then we discussed about omega average velocity, average angular velocity, and then instantaneous angular velocity. So let us discuss about the units of this angular velocity. So what are the units of this angular velocity? So as omega is equal to delta theta by delta d. Delta d is having the units radians, okay. Then second. So simply omega, the SI unit of omega is radian per second. The practical units are, as we told here, revolutions per second or degree per second. So let us discuss. For example, if a body is rotating completely for one time, means for example, let us take this circular path and this particle over here, initially here, and it has completed its rotation like this. For one rotation, what would be the angular velocity? What would be the angular displacement? So it is the radius vector, and then it has completed the rotation like this. The radius vector has completed its rotation like this. So it completes one term, one cycle. Means it is describing how much angle over 360 degrees. The 360 degrees can be written as, for example, theta is equal to some 2 pi radian or 360 degrees. So if theta is equal to 2 pi radian, and if it is completing for some time, for time period called t, after time period t, then simply omega can be written as delta theta by delta theta by delta t. So delta t is clear here. For complete rotation the angle is 2 pi radians. For complete rotation the time period is t. So here we can describe one more relation called omega, means angular velocity is equal to 2 pi by t, 2 pi by time period, or simply the units are radian per second. This is radian and then per second. And dimensions, what about the dimensions? Angular displacement has no dimension, dimension of omega. So here simply dimension, for dimension of this angular displacement is not there, but only for time it is there. So t power minus 1. For that simply we can write for this theta, the dimensions of theta as t power 0 also you can write, or m power 0, l power 0, t power 0 also we can write. And this velocity, for example, take the same rigid body, and if this angular velocity also changing with time, as this angular displacement is changing with time, we have introduced angular velocity. If this angular velocity is also changing with time, then we can introduce one more physical quantity called angular acceleration. Its symbol is alpha. In the same manner as we have discussed the definition in earlier classes, the alpha can be told as omega 2 minus omega 1 by t2 minus t1, the change in angular velocity by change in time interval, the time interval simply. So it is nothing but delta omega by delta t. If you go for the units, the SI unit simply radian per second square, already radian per second by second, that is the radian per second square, and the dimensional formula of this angular acceleration is m power 0, l power 0, and velocity is t power minus 1 now, so acceleration will be t power minus 2, or simply t power minus 2 also we can write. So this is the rotational kinematics of the rigid body. And moreover, we can describe the relations over here also. For example, in linear kinematics, we have discussed about velocities and displacements and accelerations, and we have some relations also over there. And here, if you write the analogous quantities over, just I want to mention analogous quantities here simply. So in a linear kinematics, physical quantities I will write over here, and this is angular kinematics or rotational kinematics, or rotational kinematics. Just I will give a list of physical quantities over here. So here we discussed about displacement, then here we discussed about angular displacement. This displacement is a vector, then what about this?